Welcome to this video on solving LeetCode problem number 1743, restore the array from adjacent pairs. In this problem, we are given a set of adjacent pairs, and the goal is to reconstruct the original array. We'll explore the logic and techniques needed to solve this problem step by step. Let's get started. In this problem, you are given a 2D array called adjacent pairs, where each pair represents two integers that are adjacent to each other in an array we need to reconstruct. The task is to restore and return the original array based on these adjacency relationships. To achieve this, the reconstructed array must meet a few important conditions. First, the array must consist of unique integers, no duplicates are allowed. Second, each pair and adjacent pairs must reflect the actual adjacency between elements in the restored array. Lastly, the length of the restored array must be exactly 1 greater than the number of pairs in adjacent pairs. This means that if we're given m pairs, the restored array must contain m plus 1 elements. The input consists of this 2D array of integer pairs, and the output should be a list of integers representing the reconstructed array that satisfies these conditions. Let's look at an example to better understand. Suppose the input adjacent pairs is 2, 1, 3, 4, 3, 2. This tells us that 2 is adjacent to 1, 3 is adjacent to 4, and 3 is also adjacent to 2 in the original array. Based on these relationships, the restored array would be 1, 2, 3, 4. Here's why: 1 is adjacent to 2, 2 is adjacent to 3, and 3 is adjacent to 4, so all pairs are satisfied. There's no other valid arrangement that meets these adjacency rules, making this the unique solution. This example illustrates how we use the relationships in adjacent pairs to determine the order of elements in the restored array. Here's another example. If the input adjacent pairs is 4, minus 2, 1, 4, dash 3, 1, the restored array would be dash 2, 4, 1, minus 3. Let's break it down step by step. The pair 4, minus 2 tells us that 4 is adjacent to minus 2, and the pair 1, 4 tells us that 4 is also adjacent to 1. Additionally, the pair dash 3, 1 tells us that 1 is adjacent to minus 3. When we connect these relationships, we get the array dash 2, 4, 1, minus 3. This satisfies all the adjacency requirements because minus 2 is next to 4, 4 is next to 1, and 1 is next to minus 3. Finally, consider the simplest case where adjacent pairs contains only one pair, such as 100,000 minus 100,000. Here, the restored array will simply be 100,000 minus 100,000, since there's no other way to arrange the numbers. The constraints of the problem ensure that the solution is always unique. Speaking of constraints, note that the length of adjacent pairs will always be 1 less than the length of the restored array. Additionally, the integers can range from minus 10 to the power of 5 to 10 to the power of 5, and the input size can go up to 10 to the power of 5 pairs, which means our solution must be efficient to handle large inputs. Edge cases include having only one pair, as we just saw, or working with negative and zero values, all of which the solution must account for. To solve LeetCode problem number 1743, restore the array from adjacent pairs, we aim to reconstruct the original array given a set of adjacent pairs. This challenge can be approached using graph-related concepts, as each pair represents a connection between two elements. One of the initial ideas we explored was a brute force method. The intuition behind this approach is to generate all possible permutations of the given adjacent pairs and check each one to see if it forms a valid array. For an array to be valid, two conditions must be met. Firstly, every pair from the input must appear as consecutive elements, and secondly, the array must have no duplicates, with its length equal to the number of unique elements. However, this method is highly inefficient. Generating all permutations has a factorial complexity, O(n), and verifying each permutation adds an additional O(n) factor. This results in an overall complexity of O(n)(n), which quickly becomes computationally infeasible for larger inputs, especially since the constraints allow for up to 10 to the power of 5 elements. Thus, while conceptually straightforward, this approach is not practical for real-world scenarios. Instead, we turn to an optimized graph-based approach. Here, we treat the adjacent pairs as an undirected graph. Each number becomes a node, and each pair defines an edge between two nodes. Our goal is to reconstruct the array by finding the path that traverses all nodes exactly once, essentially reconstructing the graph as a straight line. A key observation is that the endpoints of the array must correspond to nodes with exactly one neighbor, or degree 1, since these nodes appear in only one pair. With this in mind, we can outline the solution in 4 steps. First, we build the graph using a default tick to create an adjacency list, where each key represents a node and its value is a list of neighboring nodes. Second, we identify the 2 endpoints by finding the nodes with degree 1. Third, starting from one of these endpoints, we use a depth-first search (DFS) to traverse the graph and construct the array, ensuring that no node is revisited. Finally, the reconstructed array is returned as the result. This approach is both systematic and efficient, leveraging the structure of the graph for scalability. The graph-based method is efficient, with a time complexity of O(n), where n is the number of elements in adjacent pairs. Constructing the graph requires O(n), finding the endpoints is O(n), and traversing the graph via DFS is also O(n). The space complexity is similarly O(n), given the adjacency list and the visited nodes. When comparing this approach to the brute force method, the optimized strategy is far superior as it scales well and avoids the factorial complexity of permutations. Between DFS and BFS for traversal, both are viable. DFS is often simpler to implement recursively, while BFS requires managing a queue. For this solution, we selected DFS for its straightforward implementation. Although the graph-based solution requires extra memory for storing the adjacency list and tracking visited nodes, this overhead is negligible within the given constraints. The pivotal realization, or aha moment, in this problem lies in understanding that reconstructing the array is equivalent to finding a path in a graph where the endpoints are nodes with degree 1. This insight transforms what initially seems like a combinatorial problem into a clear and efficient graph traversal task. By framing the problem as a graph traversal and leveraging the properties of endpoints and connectivity, we arrive at a solution that is both elegant and scalable. This strategy not only handles large inputs efficiently but also highlights the power of graph theory in solving seemingly unrelated problems. The combination of building a graph, identifying endpoints, and using DFS to traverse ensures that the array is reconstructed accurately and optimally. This approach demonstrates the importance of recognizing underlying structures in problem solving, allowing us to simplify complex challenges into manageable steps. In this problem, we are given a list of adjacent pairs, where each pair represents 2 consecutive elements in the original array. Our goal is to reconstruct the original array from these pairs and return it. To solve this, we can think of the problem as a graph where each number in the array is a node and each adjacent pair forms an edge between 2 nodes. The challenge then becomes finding the path in this graph that represents the original array. Key insights include understanding that the original array forms a simple path, meaning there are no cycles, and that nodes with only one edge, or degree 1, correspond to the start or end of the path. This makes it possible to optimize the solution by identifying a degree 1 node to begin constructing the path. Using adjacency lists to represent the graph allows for efficient traversal and path reconstruction. An adjacency list is an efficient way to represent the graph. It is a dictionary where each key is a node, and its value is a list of neighboring nodes. Additionally, we use a visited set to track which nodes have already been processed to avoid revisiting them. The algorithm proceeds in 4 main steps. First, we build the graph by parsing the input pairs and populating the adjacency list. For each pair, we add both numbers as keys and update their respective neighbors. We also track the degree of each node, which is simply the size of its adjacency list. Next, we identify a starting node by finding any node with degree 1, as this must be either the start or the end of the path. Then, we reconstruct the path by initializing the result array with the starting node and performing a graph traversal, such as depth-first search or breadth-first search. During traversal, we add neighbors in sequence to the result array while marking nodes as visited. Finally, after all nodes have been visited, we return the result array, which will contain the original order of the elements. To illustrate these steps, consider the example input, adjacent pairs, 2, 1, 3, 4, 3, 2. First, we build the adjacency list by processing each pair. For instance, the pair 2, 1 creates a connection between 2 and 1, and the pair 3, 4 does the same for 3 and 4. After processing all pairs, the adjacency list looks like this: 2 is connected to 1 and 3, 1 is connected to 2, 3 is connected to 4 and 2, and 4 is connected to 3. Next, we identify the starting node by looking for a node with degree 1. In this case, 1 has only one neighbor, so it is the starting node. This setup allows us to begin reconstructing the path efficiently. Starting with the node 1, we initialize the result array as 1. From here, we traverse the graph. The first neighbor of 1 is 2, so we visit 2 and add it to the result array, making it 1, 2. Next, we move to 2's neighbors. Since 1 has already been visited, we proceed to 3, adding it to the result array to get 1, 2, 3. From 3, we visit its unvisited neighbor, 4, resulting in the final array 1, 2, 3, 4. At this point, all nodes have been visited, and the traversal is complete. The reconstructed array 1, 2, 3, 4 is returned as the result. This process runs efficiently, with a time complexity of O(n) for building the adjacency list and performing the traversal, and a space complexity of O(n) for storing the adjacency list in visited set. The algorithm also gracefully handles edge cases, such as single pairs or negative numbers, and ensures that disconnected graphs are invalid inputs. Several key optimizations make this algorithm efficient. Representing the graph as an adjacency list ensures that we can query neighbors and traverse the graph in constant time per edge. Starting from a degree 1 node eliminates unnecessary checks and guarantees that our traversal begins at one endpoint of the path. Using a visited set prevents redundant processing and ensures that each node is added to the result array exactly once. Together, these optimizations enable the algorithm to handle even large inputs effectively while maintaining clarity and correctness in reconstructing the original array. Here, we start by importing the necessary modules. We use defaultDict from the collections module to create an adjacency list for the graph, and Dict to help us implement a breadth-first search, or BFS, later on. Next, we define the restoreArray method inside the solution class. The first step in solving the problem is to construct the graph using the given adjacent pairs. For each pair of numbers in the input, we add them as neighbors to each other in the adjacency list. This creates a bidirectional graph where each node points to its adjacent nodes. In the second step, we identify one of the endpoints of the array. An endpoint is a node in the graph that has only one neighbor, meaning its degree is 1. We iterate through all the nodes in the graph and check their degree. As soon as we find an endpoint, we store it in the variable start and break out of the loop. This gives us a starting point for reconstructing the array. Finally, we initialize the variables needed for BFS, an empty list called result to store the reconstructed array, a visited set to keep track of the nodes we've already processed, and a queue initialized with the starting node. Now, we proceed with the BFS to reconstruct the array. While there are nodes in the queue, we process them one at a time. The current node is dequeued and checked to see if it has already been visited. If it has, we skip it and move on to the next iteration. Otherwise, we append the current node to the result list and mark it as visited by adding it to the visited set. Next, we loop through all the neighbors of the current node. For each neighbor that hasn't been visited yet, we add it to the queue to be processed later. This ensures that we explore the graph layer by layer, visiting each node exactly once. Once the BFS completes and the queue is empty, the result list will contain the reconstructed array in the correct order. Finally, we return the result as the output. Here, we start by defining the restoreArray method, which will reconstruct the original array from the given adjacent pairs. First, we need to construct a graph using an adjacency list. We use a hash map where each key represents a node, and its value is a list of adjacent nodes. For every pair in the adjacent pairs array, we add both elements to each other's adjacency list. This ensures that the graph accurately represents all connections. Next, we identify one of the endpoints of the array. An endpoint is a node that has only one adjacent neighbor, its degree is 1. To find this, we iterate over the graph's entries. When we find a node with a single neighbor, we designate it as the starting point for our reconstruction process. This node is stored in the start variable. Now, we're ready to reconstruct the array using a breadth-first search (BFS) approach. We calculate the size of the result array as n, which is one more than the number of pairs, and prepare supporting data structures like a hash set to track visited nodes and a queue to manage the BFS process. We initialize the queue with the starting node to begin traversal. To reconstruct the array, we use a while loop that continues as long as the queue is not empty. Inside the loop, we pull the first element from the queue. If this node has already been visited, we skip it to avoid cycles. Otherwise, we add it to the result array at the current index and increment the index. We also mark the node as visited by adding it to the visited set. Next, we iterate through all the neighbors of the current node by accessing its adjacency list in the graph. For each neighbor, if it hasn't been visited yet, we add it to the queue so it can be processed in subsequent iterations. This ensures that we traverse all nodes in the correct order. Once the loop completes, the result array contains the restored sequence, which we then return as the final output of the method. To begin solving the problem, we first need to build a graph representation using the given adjacent pairs. For the input 2, 1, 3, 4, 3, 2, we construct an adjacency list. Each key in this list represents a node, and its values are the nodes directly connected to it. After processing all pairs, the graph becomes 2, 1, 3, 1, 2, 3, 4, 2, 4, 3. This adjacency list will help us understand the relationships between the nodes. Next, we identify an endpoint, which is a node with only one neighbor, as it must be one of the ends of the original array. Scanning the graph, we see that node 1 and node 4 each have only one neighbor. Thus, we can choose one as our starting point. With this starting point, we can now reconstruct the array by traversing the graph using breadth-first search, or BFS. We initialize an empty set for visited nodes, a queue starting with our endpoint 1, and an empty list to store our result. We begin the BFS traversal with the first node, 1. Dequeuing 1 from the queue, we add it to the result list, which now becomes 1, and mark it as visited. Looking at its neighbors in the graph, we find that 2 is unvisited, so we add 2 to the queue. Moving on to 2, we dequeue it, append it to the result to get 1, 2, and mark it as visited. Checking its neighbors, we find 3 is unvisited and add it to the queue. Next, we process node 3 by dequeuing it, adding it to the result 1, 2, 3, and marking it as visited. From its neighbors, 4 is unvisited, so we enqueue 4. Lastly, we visit node 4, dequeuing it, appending it to the result 1, 2, 3, 4, and marking it as visited. Since 4 has no unvisited neighbors, the queue is now empty, and we have successfully reconstructed the array. With the queue empty, our final reconstructed array is 1, 2, 3, 4, which is the correct order of nodes based on the adjacency pairs. Now, let's move on to another example to reinforce our understanding. For the input 5, 6, 6, 7, 8, 7, we start by building the graph. After processing all the pairs, the adjacency list becomes 5, 6, 6, 5, 7, 7, 6, 8, 8, 7. Next, we identify an endpoint by scanning for a node with only one neighbor. Here, node 5 and node 8 each have one neighbor, so we can choose 5 as the starting point. With this starting node, we are ready to reconstruct the array using BFS. We initialize our BFS traversal with an empty visited set, a queue containing the starting node 5, and an empty result list. Starting with node 5, we dequeue it, append it to the result 5, and mark it as visited. Its only unvisited neighbor, 6, is added to the queue. Next, we process node 6 by dequeuing it, adding it to the result 5, 6, and marking it as visited. From its neighbors, 7 is unvisited, so we enqueue 7. Moving on to node 7, we dequeue it, append it to the result 5, 6, 7, and mark it as visited. Its unvisited neighbor 8 is added to the queue. Finally, we visit node 8, dequeue it, and add it to the result 5, 6, 7, 8. We also mark it as visited. Since 8 has no unvisited neighbors, the queue is now empty, and our traversal is complete. At this point, the reconstructed array is 5, 6, 7, 8. This matches the expected order of nodes based on the adjacency pairs given in example 2. Let's examine one more example to see how the algorithm performs with a simpler input. For the input 10, 20, 20, 30, we construct the graph by adding each pair, resulting in the adjacency list 10, 20, 20, 10, 30, 30, 20. We then identify an endpoint, a node with one neighbor. In this case, node 10 and node 30 each have one neighbor. We choose 10 as our starting point and proceed to reconstruct the array using BFS. We begin the BFS traversal for this example with an empty visited set, a queue initialized with 10, and an empty result list. Starting with node 10, we dequeue it, append it to the result, 10, and mark it as visited. Its unvisited neighbor, 20, is then added to the queue. Next, we process node 20. Dequeuing it, we append it to the result, 10, 20, and mark it as visited. Among its neighbors, 30 is unvisited, so we enqueue 30. Finally, we visit node 30, dequeue it, append it to the result, 10, 20, 30, and mark it as visited. With no unvisited neighbors left, the queue becomes empty, and the traversal concludes successfully. In all three examples, the algorithm demonstrates its ability to accurately reconstruct the array by first identifying an endpoint and then traversing the graph using BFS. This approach ensures that the nodes are visited in the correct order, respecting the relationships defined by the adjacency pairs. By following these steps, we can reliably solve the problem for any valid input of adjacent pairs. To analyze the time complexity of the solution, we can break it down into three main steps. First, we need to build the graph from the given adjacent pairs. This involves iterating through the adjacent pairs list, which has a size of n. For each pair, A, B, we add both A and B to the adjacency list, and since we process each pair once, this step takes O, n. Next, we need to find one of the endpoints of the array. This requires iterating over all the keys in the adjacency list, which represent the unique nodes in the graph. Since the restored array has n plus 1 unique nodes, this step takes O, n plus 1, which simplifies to O, n. Lastly, we reconstruct the array using a breadth-first search, or BFS. During BFS, each node is visited exactly once, and its neighbors are processed. With n plus 1 total nodes, this step also takes O, n plus 1, which simplifies to O, n. Each of these steps is linear in complexity, so they contribute to an efficient solution overall. When we combine all the steps, the total time complexity of the solution is O, n, from building the graph, plus O, n, from finding an endpoint, and another O, n, from reconstructing the array using BFS. Adding these together gives us an overall time complexity of O, n. Now, if we look at the space complexity, it is determined by several contributing factors. First, we store the graph as an adjacency list, where each node maintains a list of its neighbors. With n pairs, the graph ends up having n plus 1 nodes and 2n edges, resulting in a space requirement of O, n. Then, we have a visited set used during BFS to keep track of which nodes have already been processed. In the worst case, this set will contain all n plus 1 nodes, which requires another O, n, space. Together, these two components contribute significantly to the overall space complexity. In addition to the graph and the visited set, space is also used by the BFS queue. The queue temporarily stores the neighbors of the current node being processed, and in the worst case, its size is bounded by the number of nodes, which is O, n. Finally, there is the result list, which holds the restored array. Since the restored array contains n plus 1 elements, the space required for this list is also O, n. When we add up all these components, the graph, the visited set, the queue, and the result list, we find that the total space complexity of the solution is O, n, plus O, n, plus O, n, plus O, n, which simplifies to O, n. Both the time and space complexities are linear, making the solution highly efficient for large inputs. To put this into perspective, we can compare the current solution to a brute force approach. A naive solution would involve generating all possible permutations of the nodes and checking if each permutation satisfies the adjacency conditions. Generating these permutations would take O, n plus 1. And verifying each permutation would take O, n. This results in a time complexity of O, n plus 1. Asterisk n, which is computationally infeasible for even moderately large inputs. In contrast, the optimal solution we've discussed uses graph theory and BFS to reduce the time complexity to O, n, which is a dramatic improvement. This efficiency is possible because the adjacency list ensures that every node and edge is processed exactly once during graph construction and BFS. With n+1 nodes and 2n edges, the total work is proportional to n, ensuring that the algorithm runs in linear time and uses linear space, both of which are O(n). One common mistake when solving this problem is not handling edge cases for small inputs. For instance, if the input only contains 2 adjacent pairs or the restored array has a length of just 2, overlooking these cases can lead to index errors or incorrect outputs. To address this, it's important to always test your solution with the smallest possible input sizes to ensure proper handling of edge cases. Another frequent pitfall is constructing the graph incorrectly, such as treating it as directed when it should be undirected. Since each adjacent pair represents a bidirectional relationship, you need to store both directions in your graph representation, typically using a dictionary. Inefficiency in traversal is also a problem to watch out for. Using brute force to find the starting element or reconstruct the array can quickly escalate the complexity to O(n²). To avoid this, use a hash map for adjacency lists and take advantage of O(1) lookups for efficient traversal. Another challenge arises when failing to identify the correct starting point of the array. Remember, the starting element is the node with only one neighbor. If this isn't explicitly checked, you might begin the reconstruction from the wrong point and generate an incorrect result. To prevent this, ensure your logic includes a step to identify nodes with just one connection. Additionally, mismanaging visited nodes during traversal can result in cycles or duplicate elements in the restored array. To handle this, use a set or a Boolean array to keep track of nodes that have already been visited. This ensures that each node is processed exactly once, maintaining the integrity of the reconstruction process. This problem is a classic example of reconstructing a path from adjacency information, which is a key graph pattern. Recognizing that the pairs form an undirected graph is critical to solving it correctly. One insightful observation is that the start of the array corresponds to a node with only one neighbor. Identifying this simplifies the logic significantly and sets the foundation for successful traversal. It's also important to be comfortable explaining different traversal methods, such as DFS and BFS, and understanding their trade-offs. While DFS is often simpler to implement for this problem, you may be asked to justify your choice during an interview. Additionally, be prepared to discuss how your solution handles edge cases, like very small arrays, disconnected graphs, or invalid input, as these are common points of discussion. This problem is closely related to several others on LeetCode. For example, LeetCode 332, Reconstruct Itinerary, involves reconstructing a path from tickets and emphasizes ordering, which is similar in structure. Another is LeetCode 261, Graph Valid Tree, which focuses on verifying connectivity and acyclic properties of a graph, concepts that are foundational to understanding traversal. LeetCode 721, Accounts Merge, involves merging data based on shared connections, and LeetCode 323, Number of Connected Components in an Undirected Graph, emphasizes traversal and connectivity. These problems build intuition for solving graph-based challenges like this one. As for alternative approaches, a brute force method could reconstruct the array by repeatedly searching for pairs, but this would lead to O(n²) complexity. While simple to implement, it's not efficient for larger inputs. Instead, a DFS-based reconstruction offers a time complexity of O(n), and is both efficient and straightforward, though you must carefully manage visited nodes to avoid cycles. A BFS-based reconstruction is another effective approach, working similarly to DFS but using a queue to iteratively reconstruct the array. This method is equally efficient, with a time complexity of O(n). It's often preferred when iterative solutions are required, even though it can be slightly more verbose than DFS. On the other hand, it's important to avoid overcomplicating the problem with unnecessary techniques like topological sorting. While topological sorting works for directed acyclic graphs, it's not applicable here since the graph is undirected. Adding such complexity can lead to confusion and wasted effort. By focusing on the simplicity of DFS or BFS, you can solve the problem efficiently and with clarity. Great job! We've walked through how to solve LeetCode number 1743 by leveraging hash maps to reconstruct the original array. Remember, understanding the relationships between elements is key to solving similar problems. If you enjoyed this video, please like, share, and subscribe for more helpful solutions. See you next time, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!